Through the void, where silence is older than light itself, a cloud of fire breathes. It is the Orion Nebula, a wound in the fabric of night, glowing with the colors of creation. From Earth it appears soft, tranquil, almost tender, a patch of faint luminescence nestled in the hunter's sword. Yet that glow is not peace. It is violence slowed by distance, an explosion stretched across centuries, a storm of radiation, gravity, and dust so vast it could swallow entire solar systems and still hunger for more. What we see as beauty is the universe caught in the act of tearing itself apart to build anew. Inside that shimmering veil, chaos reigns. Clouds of hydrogen and helium collapse under the invisible pull of gravity, grinding and folding into knots of heat and density until atoms themselves begin to fuse. In those cores, nuclear fire ignites not softly, but with the fury of 1,000 suns being born at once. The light that escapes is the residue of battle, photons clawing their way through fields of dust that will one day form worlds. This is the paradox of Orion, the nursery of stars that shines, because of its own destruction, stretching more than 24 light-years across and lying 1,300 light-years away. The Orion Nebula is not a single object, but a living system, a tapestry of stellar wombs, magnetic storms, and shock waves echoing through eternity. It is a monument to both scale and intimacy. Through the eyes of Hubble and Webb, what was once a blur of mist becomes a cathedral of light, where filaments of plasma twist like the veins of a living being. In its heart, for monstrous suns known as the Trapezium blaze together, their radiation carving caverns in the gas around them. Their light sculpts the nebula's walls into shapes of ghostly brilliance, their winds shredding and scattering the very matter from which new stars attempt to form. Even in birth, they destroy the future of others. If wonder still calls to you, subscribe and let the unknown guide us forward. Every pulse of that light is a memory written in heat. The dust glows, not because it is alive, but because it has been struck, energized, ionized, wounded, and yet within these wounds, the seeds of worlds coalesce. Around the younger stars, disks of dust are gathering, spinning, condensing the raw material of planets like our own. Somewhere in that luminous maelstrom, the story of Earth has already played out 1,000 times, unseen. But what does it mean that the universe builds through such violence? That every atom in every human hand was once forged in the heart of such storms? If all creation requires destruction, if every act of becoming is born of breaking, then perhaps chaos is not the enemy of order, but its architect. And so, beneath the tranquil glow that adorns our night sky, astronomers began to see something far deeper than beauty. They saw a truth, both ancient and unsettling, that within Orion's brilliance lies the story of how the universe itself is born not in peace, but in fire. And so they turned their gaze toward this luminous abyss, not for its splendor, but for what it conceals, the secret of how creation and destruction are, and have always been, the same thing. Long before the first lens was ground or the first equation written, Orion ruled the night as myth. To the ancients, he was the hunter, the eternal figure drawn in stars, chasing the bull across the black expanse of heaven. His belt, 3 perfect points of light, guided sailors across unknown seas and marked the changing of seasons for farmers who looked to the sky for order. But hidden between those bright sentinels lay a faint, milky glow, a cloud so soft it escaped attention for centuries. It was no god, no hunter, no myth. It was something far older, far more primal, the universe, mid-breath, forming the very stars that once defined him. When Galileo turned his telescope toward Orion in the early 17th century, he expected clarity. What he found instead was a mystery deepened, where the naked eye saw only a haze. His crude lenses revealed a scatter of stars emerging from mist, a curtain parting slightly to expose creation itself. The glow was not empty, it was a forge, yet the instruments of his age could only hint at its magnitude. The Orion Nebula would remain a whisper, a spectral question, until centuries later when technology caught up to the wonder it hid. In the 19th century, photography began to replace the human eye. The first astrophotographs captured Orion not as a pattern of stars, but as an unfolding structure, filaments of gas, tangled and immense. Astronomers realized they were not looking at a simple cloud, but a dynamic system in motion light years across. It was as if the sky itself had been caught in the act of creation. Spectroscopy confirmed it. Orion was rich in hydrogen, the universe's most abundant element, the very fuel of stars. The nebula, once myth, became physics. Then came the era of space telescopes, Hubble first, then Spitzer, then Webb, each peeling back another layer of light. Hubble's sharp eyes revealed turbulent pillars, shock fronts, and cavities sculpted by stellar winds. Inside, it found the Trapezium Cluster, four massive suns less than 1,000,000 years old, burning so intensely they reshaped the nebula around them. Their ultraviolet radiation ionizes the surrounding hydrogen, causing it to glow in hues of pink and violet. What the human eye perceives as beauty is, in truth, a constant battle of energy, radiation carving through matter, like fire through mist. Yet even Hubble's gaze was limited. The densest regions of Orion, where the youngest stars were still cocooned in dust, remained hidden. It took the James Webb Space Telescope, with its infrared vision, to finally pierce the veil. Webb revealed the invisible, hundreds of infant stars, some barely a few thousand years old, still wrapped in their dusty envelopes. Around them, disks of gas and debris spun the blueprints of future planets. What had once been a mythic hunter had become something even more profound, a cosmic womb through Webb's eyes. Orion was no longer distant or abstract. It was alive, a place where time moved differently, where the past and future overlapped in the endless act of creation. Every filament of gas, every glimmer of light was a sentence in a story that began long before humanity learned to read the sky. But the deeper scientists looked, the stranger the truth became. Orion was not only a cradle of stars, it was a crucible. For every sun that ignited, countless others failed to form, crushed or scattered by the violence of their siblings. Creation here was not gentle. It was selective, ruthless, governed by chaos and gravity's iron hand. Beneath the beauty lay turmoil, the same destructive forces that give rise to life itself. And so, the myth of the hunter transformed once more. The figure in the sky was no longer chasing prey, but symbolizing the eternal pursuit of understanding, humanity's attempt to witness its own beginnings through the veil of light and dust. Yet this revelation carried a darker edge. For every star born in Orion's glow, hundreds perish unseen, extinguished before their first breath. To understand this violence, the balance between birth and annihilation that defines the cosmos, astronomers would have to go beyond what even Webb could see. They would have to descend deeper into the heart of the storm itself, where gravity and time twist together to write the rules of existence. For within Orion's beauty lies a secret the universe still keeps, that creation and destruction are not opposites. They are the same act, viewed from different ends of light. The data from Webb and other observatories transformed Orion from a familiar patch of night sky into a laboratory of astrophysics. What had once been a vague, glowing cloud now resolved into a complex and measurable system, an engine that converts diffuse gas into stars, through well-defined but still poorly understood physical processes. Within its 24 light-year span, the nebula contains roughly 2,000 times the mass of our Sun in gas and dust. Observations show temperatures reaching 10,000 degrees Kelvin in its ionized regions, while colder, denser molecular clouds nearby hover just above absolute zero. This gradient of temperature and density provides the stage for star formation, where gravitational instability pushes matter toward collapse. High resolution spectroscopy and radio mapping have revealed that Orion's structure is not uniform. It is stratified into filaments and bubbles, each shaped by the feedback of young, massive stars. The radiation and stellar winds from the Trapezium Cluster erode surrounding gas, creating cavities and fronts that ripple outward at supersonic speeds. These waves compress nearby regions, triggering new rounds of collapse and starbirth, a cycle of feedback that ensures Orion remains active. Astronomers refer to this as sequential star formation, where one generation of stars creates the conditions for the next. Within these regions, ALMA, the Atacama Large Millimeter, Submillimeter Array, has detected more than 500 protoplanetary disks, flattened, rotating structures of gas and dust around newborn stars. Each disk represents a possible future solar system, with grains colliding and growing into pebbles, rocks, and planetesimal. Some may already harbor the first outlines of planets, though their development is constantly threatened by the intense ultraviolet radiation from nearby massive stars. These external forces can strip disks of their outer layers, evaporating volatile materials before planets can form. One reason Orion is considered both fertile and hostile. The Trapezium Cluster itself dominates the dynamics of the nebula. The four primary stars, each 15 to 30 times more massive than the Sun, produce stellar winds that travel at thousands of kilometers per second. These winds collide with ambient material, forming shock fronts visible in multiple wavelengths. X-ray observations from the Chandra Observatory have mapped these high-energy interactions, revealing temperatures exceeding 10 million degrees. The pressure from this hot gas drives the expansion of Orion's central cavity and reshapes the nebula continuously on astronomical timescales. Through computer simulations, researchers now attempt to reproduce Orion's evolution, combining gravity, radiation, and magneto. The results suggest that turbulence plays a central role. Rather than forming smoothly, stars emerge from turbulent flows that create dense pockets in an otherwise chaotic environment. These models align with observed velocity fields inside the nebula, where gas moves in multiple directions simultaneously, defying simple collapse models. Magnetic fields, though weak, appear to help regulate this chaos, guiding material along invisible lines and delaying collapse in some regions while accelerating it in others. Despite decades of study, many parameters remain uncertain. The precise rate of star formation, the efficiency of gas-to-star conversion, and the lifespan of dense clumps within Orion are still active areas of research. Infrared time-lapse data now tracks changes in brightness around young stellar objects, offering the first glimpse of star formation as a dynamic, time-dependent process rather than a static image. Even with this progress, the balance between constructive and destructive forces in Orion remains delicate. Too much radiation or turbulence, and clouds disperse before stars can form. Too little, and collapse becomes inefficient. The scientific portrait of Orion today is a fusion of observation and computation, a model of feedback, turbulence, and gravitational interplay on a colossal scale. It stands as the closest and most accessible example of how galaxies continually recycle matter into new generations of stars and planets. By studying Orion, astronomers refine their understanding of how systems like our own solar neighborhood once emerged from similar nebular conditions. Each new dataset adds resolution to that story, reducing myth to measurable physics, while preserving the same sense of wonder that first drew ancient eyes to its light. The nebula remains a benchmark, both familiar and alien, a place where physical laws shape creation in real time, observable across the spectrum from radio waves to gamma rays. As instruments continue to improve, Orion is expected to yield more precise insights into the earliest phases of stellar evolution, not as a symbol or a legend, but as an empirical cornerstone of cosmic birth. Beneath its color and glow lies a record of the forces that built the stars themselves, still unfolding in a region of space both perilous and essential to the understanding of where every star, planet, and molecule of life begins. Amid the soft glow of Orion's vast cloud, creation unfolds with deceptive serenity. The nebula's light, visible from hundreds of light-years away, suggests beauty and peace, a cradle for newborn stars shimmering behind curtains of gas and dust. But beneath that radiance lies a far more complex truth. Orion is not a nursery of calm beginnings. It is a theater of chaos, where gravity and energy wage an endless war between collapse and destruction. Every flicker of light is both a birth cry and an echo of something torn apart. At the heart of this cosmic storm, immense clouds of hydrogen drift like silent oceans. Over millions of years, gravity gathers them, compressing the faintest whispers of matter until density crosses a critical threshold. The gas folds inward, heating as it falls, spiraling toward a point of no return. Deep within, the temperature climbs to millions of degrees, and nuclear fusion, the same force that powers the sun, finally ignites. A new star is born, yet this outcome is rare. Most clouds fail before reaching ignition. Turbulence, radiation, and magnetic fields twist them apart. Waves of pressure ripple through, fragmenting them into clusters of doomed attempts. The majority of stellar seeds never become suns. They dissolve back into the nebula sea, victims of the same forces that tried to create them. In Orion, gravity's grip is both generous and merciless. The region is so dense that stars often form in close quarters, their envelopes brushing, their magnetic fields tangling like living nerves. When these young stars draw too close, they feed on each other's material, siphoning gas, stripping disks, even merging in violent collisions. Astronomers call it competitive accretion, but in truth, it is star cannibalism, a brutal hierarchy of creation where the strong grow by consuming the weak. Some of the most massive stars in Orion owe their size to this chaotic feeding, swelling beyond normal limits in an arms race of accumulation. And then there are the jets. Each newborn star, still wrapped in its shroud of dust, launches twin streams of plasma from its poles narrow. Luminous jets stretching for light years. They blaze through the nebula at hundreds of kilometers per second, carving through the clouds like cosmic spears. These outflows carry away excess momentum, allowing the star to stabilize. But they also disrupt the fragile environment around them. Where one star tries to form, another's jet may destroy the possibility. The same process that sustains creation ensures that destruction is never far behind. It is a system that regulates itself through violence, where order emerges only because of disorder. The remnants of past cataclysms still echo here. Shock waves from ancient supernova ripple invisibly through Orion's expanse, the aftershocks of stars that lived fast and died spectacularly. These shock waves compress fresh gas, triggering new rounds of star birth, proving that even death feeds the next generation. Every atom within Orion's glowing filaments has been through this cycle countless times, collapsed, burned, exploded, and reborn. The nebula is a living archive of stellar ancestry, where nothing is wasted and nothing truly ends. Yet one mystery continues to haunt astronomers. Orion produces an unusually high number of massive stars, those that burn brighter and die younger than the rest. These giants live for only a few million years, yet their presence dominates the region's dynamics. Why so many? Why here? Theoretical models struggle to explain the imbalance. Some suggest that Orion's turbulence funnels matter into the cores more efficiently, accelerating growth before feedback can halt it. Others suspect remnants of earlier supernova may have altered the density and magnetic structure of the cloud, biasing it toward heavier formation. Whatever the reason, Orion's massive stars are both creators and destroyers, lighting up the nebula even as they sculpt its doom. With each observation, the picture grows darker, more intricate. Orion is no longer a simple birthplace of stars, but a battlefield where the laws of physics fight for dominance. Gravity strives to build. Radiation strives to tear apart. Fusion ignites, only to be extinguished by its own byproducts. The deeper scientists look, the clearer it becomes. Creation in the cosmos is not a gentle process, but an act of controlled violence. And in Orion, that balance between life and death tips ever so slightly toward the edge of annihilation. The more we looked, the more Orion seemed less like a nursery, and more like a battlefield. Modern astronomical instruments have turned Orion from a distant wonder into a detailed case study of stellar evolution. Data from the Atacama Large Millimeter Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, provide insight into how gas, dust, and magnetic fields interact within its dense molecular clouds. Observations show that Orion's star-forming regions are anything but uniform. Temperatures fluctuate sharply, density varies across small scales, and turbulence constantly reshapes the gas. These irregular conditions make predicting star formation extremely difficult. Even with advanced simulations, small changes in density or magnetic alignment can determine whether a cloud forms a star or disperses before ignition. Instruments operating at different wavelengths reveal distinct aspects of the same environment. Infrared telescopes penetrate the thick dust to expose newly forming stars still hidden in their cocoons. Radio arrays map the motion of cold gas and trace molecules like carbon monoxide, which act as markers for the conditions within the cloud. X-ray observatories such as Chandra detect high-energy emissions from young, hot stars and the shock fronts created by stellar winds. Together, these observations provide a layered understanding of Orion's ecosystem, where multiple forms of energy coexist and interact in real time. The Trapezium Cluster, located near the center of the Orion Nebula, remains a focus of ongoing study. The four primary stars in the cluster, Theta, A, Orionis, A, B, C, and D, emit intense ultraviolet radiation that ionizes surrounding hydrogen, creating the nebula's characteristic glow. Their combined stellar winds push away gas at speeds exceeding 10 kilometers per second, carving cavities and triggering new waves of compression in nearby regions. This constant recycling means the nebula is always changing shape. Structures that appear stable in visible light are, in reality, temporary formations that evolve over thousands of years. Webb's recent infrared images have identified dozens of protostars previously undetected, including several that exhibit signs of forming planetary disks. These disks are early versions of solar systems, flattened structures of dust and gas orbiting young stars. Over time, they may give rise to planets, moons, and asteroids. However, in Orion, these disks exist under extreme radiation. Many are stripped of material before planets can fully form. This raises important questions about the survival rate of planetary systems in high-energy environments. If most protoplanetary disks in regions like Orion are destroyed, then the origins of systems like ours must lie in calmer, more isolated clouds. The interplay between massive stars and their surroundings is one of the nebula's most important lessons. Higher stars dominate the local energy balance, but their existence shortens the lifespan of the molecular cloud itself. The radiation and winds they release eventually disperse the material required for further star formation. In effect, massive stars terminate the very process that created them. This self-regulating mechanism may explain why stellar nurseries like Orion have relatively brief lifetimes on the cosmic scale, just a few million years before the gas dissipates into interstellar space. Researchers use computational models to test how small changes in initial conditions might reproduce Orion's characteristics. The results show that feedback from massive stars through radiation pressure, stellar winds, and supernova explosions is essential to shaping the final outcome. Without feedback, simulations produce an unrealistic abundance of low-mass stars. With feedback included, the pattern more closely matches what is seen in Orion. Fewer but larger stars, surrounded by disrupted gas. This confirms that destruction is not a byproduct but a built-in component of stellar creation. The deeper scientists probe, the more Orion resembles a closed-loop system governed by equilibrium. Gravity builds structure. Radiation erases it. Magnetic fields guide flows of matter, then collapse under the same pressure they channel. Every stage feeds into the next, maintaining a balance that keeps the nebula active yet finite. When its most massive stars reach the end of their short lives, they will explode as supernova, enriching the surrounding medium with heavier elements, the raw ingredients for the next generation of stars. The cycle continues, reshaping the nebula and seeding the galaxy beyond. Orion, once viewed as a simple collection of stars, now stands as a laboratory of astrophysical feedback, a place where every observation adds another piece to the understanding of how galaxies sustain themselves through destruction and renewal. For most of human history, Orion was not seen through the lens of science but through myth, art, and story. Its three aligned stars, Alnilam and Mintaka, formed the Hunter's Belt, a celestial signature that appeared across civilizations separated by oceans and millennia. To the Egyptians, Orion was Osiris, god of the afterlife and renewal. The three pyramids of Giza, aligned with these stars, were not merely tombs but symbolic gateways between worlds. In their geometry lay a cosmic faith that the sky above was not chaos but a map, one that traced the cycle of death and rebirth. The same intuition, born of observation and reverence, would one day evolve into something far more precise, the science of star formation. As centuries passed, the mythic Orion remained constant, but the tools of sight changed. By the time of the early telescopes, starlight was no longer sacred, it was measurable. In 1610, Galileo turned his modest instrument toward Orion and described innumerable stars, which have never been seen before. He saw what the naked eye could not, that the faint glow beneath Orion's belt was not empty space, but a veil of unresolved light, a region too complex for human vision alone. What had once been a symbol now became a puzzle. By the 19th century, that puzzle began to unfold through photography. In 1880, American astronomer Henry Draper captured the first long-exposure image of the Orion, Nebula using a 28-inch refractor telescope in New York. For the first time, humanity could see the nebula not as a ghostly blur, but as a structure, filaments of dust and gas twisting around a bright core. The photograph revealed a truth that transformed astronomy. Light could be captured, stored, and studied, even from hundreds of trillions of kilometers away. The nebula, once a mythic realm of gods, had become a physical object, one that could be measured, analyzed, and compared. Then came spectroscopy, the science of decoding light. In the early 20th century, scientists like Annie Jump Cannon and Cecilia Pangaposhkin discovered that when light from a star is split into a spectrum, it reveals a distinct pattern of lines, fingerprints of elements: hydrogen, helium, carbon, the same ingredients that build Earth, oceans, and living cells. This revelation closed the distance between humanity and the stars. Orion's light was not alien. It was familiar. The nebula's swirling clouds contained the same atoms found in human breath and blood. The ancient belief that humanity was born of the heavens found its scientific counterpart in the language of spectral lines. The mid-20th century marked another leap. As telescopes grew larger and reached higher into the atmosphere, the veil of Earth's distortion thinned. Then came space-based observatories, first Hubble, then Spitzer, and now the James Webb Space Telescope. Each new eye stripped away another layer of mystery. Hubble's optical clarity revealed Orion as a chaotic ecosystem, young stars tearing through gas, carving tunnels of light. Spitzer, observing in infrared, saw deeper still, identifying warm dust and hidden structures invisible to human eyes. Webb's infrared mirrors now reach beyond both, capturing embryonic stars before they pierce the dark with their first light. Through these missions, Orion ceased to be a static nebula. It became a living process, a machine of creation and destruction, operating across millions of years. Hubble's 2006 survey identified more than 3,000 young stars within its boundaries. Later, Spitzer and Alma discovered hundreds of protoplanetary disks, each one a potential solar system in formation. These proplyds, as astronomers call them, are fragile and fleeting, thin rings of dust surrounding infant suns, often scorched by nearby radiation before they can form planets. Each advancement from myth to telescope, from film plate to infrared array, refined not only what humanity saw, but what it asked. Early astronomers wondered what the nebula was. Modern scientists now ask how it works, how clouds of hydrogen become stars, how the violence of radiation and gravity coexists with the order of formation. Orion transformed from a constellation of myth to a laboratory of physics, and yet, beneath all the data, one thread remains unchanged. The same wonder that guided the builders of Giza now fuels researchers operating instruments. Millions of miles from Earth, the questions are sharper, the tools more powerful, but the impulse is the same: to understand what connects the chaos of the cosmos to the order of life. Each observation of Orion deepens the paradox. The nebula is both creator and destroyer, sculptor and storm. The violent conditions that tear its disks apart are the same that forge the heavy elements from which worlds are built. Hydrogen, fused in the hearts of its stars, becomes the oxygen we breathe and the carbon that builds our cells. Out of destruction comes chemistry. Out of fire comes form. And so, the human story and Orion's story converge. Both are born from collisions. Both evolve through transformation. Both seek balance within chaos. The more clearly we see Orion, the more it reflects us, a mirror of creation's restless drive. The question is no longer what Orion is, but why it behaves this way. Why does it form so many massive, short-lived stars when the galaxy could sustain quieter, steadier ones elsewhere. The next chapter of exploration would turn from the tools of observation to the forces behind them, to the physics that govern how the universe chooses to build itself. And behind every photograph, every spectrum, every pixel of light, lingers a deeper question. Could this violence be the very reason we exist? As data from modern observatories accumulated, Orion became one of the most studied regions in the entire Milky Way. Astronomers treated it as a controlled environment, a nearby laboratory where the physics of star formation could be directly observed and compared to theoretical models. Its proximity, only about 1,344 light-years from Earth, made it ideal for detailed analysis. High-resolution instruments like ALMA, operating in Chile's Atacama Desert, measured the motion of gas within the nebula with precision. By tracking shifts in the frequency of emitted radiation, scientists could map turbulence, temperature gradients, and areas of gravitational collapse. This provided an unprecedented look into how molecular clouds evolve into clusters of stars. What they found was a process far more dynamic and unstable than early models predicted. Instead of a smooth, steady collapse, the gas in Orion moves chaotically. Supersonic turbulence, magnetic interference, and shock fronts from nearby stellar winds create an environment of constant disruption. This means that only a small fraction of the material in a molecular cloud actually becomes part of a star. The rest is expelled back into space, either by radiation pressure or mechanical feedback from newly formed stars. These findings explain why, even in such a massive nebula, star formation efficiency rarely exceeds a few percent. Detailed spectral analysis of Orion's gas composition further refined understanding of the nebula's evolution. Hydrogen remains the dominant element, but traces of heavier atoms, oxygen, nitrogen, sulfur, and silicon, indicate that earlier generations of stars once lived and died in the same region. The presence of these elements suggests that Orion is a product of multiple stellar cycles. Older supernova remnants seeded the area with the materials now forming new stars. This recycling process highlights how galactic chemistry evolves over time, creating the conditions necessary for planets and life elsewhere. Advancements in computational astrophysics have complemented these observations. Researchers now run three-dimensional simulations of Orion's environment using high-performance computing systems, incorporating gravity, magnetic fields, and radiative transfer. These digital models replicate many of the observed features: collapsing elements, clustered star formation, and the effects of massive stellar feedback. However, the models still struggle to reproduce the full complexity of what telescopes record. Real molecular clouds are influenced by unpredictable variables such as cosmic ray interactions, chemical reactions in dust grains, and microscale turbulence factors, difficult to simulate even with current technology. The James Webb Space Telescope has added another layer to this understanding by revealing hundreds of embedded protostars invisible to previous instruments. Its infrared sensors detect faint emissions from warm dust around these forming stars, allowing scientists to study the earlier stages of collapse before fusion begins. Some of these protostars exist in tightly packed clusters, suggesting that gravity alone cannot explain their distribution. Magnetic fields likely play a larger role than once assumed, guiding the flow of material along invisible lines of force and shaping the birthplaces of new stars. In addition to stellar dynamics, Orion has become essential for studying planet formation. Many of the protoplanetary disks discovered in the nebula show evidence of erosion caused by ultraviolet radiation from nearby massive stars. This destructive influence limits the lifespan of disks and may prevent full planetary systems from developing. The discovery challenges earlier ideas that planet formation is universal in all star-forming regions. It now appears that only certain environments, those shielded from intense radiation, are capable of sustaining the process long enough for stable planets to form. The combined findings from spectroscopy, imaging, and simulation point to a clear conclusion. Orion's environment is efficient at producing large, short-lived stars, but poor at sustaining long-term planetary systems. The nebula's extreme conditions, dominated by radiation and turbulence, favor high-mass star formation while suppressing smaller, quieter ones. Understanding why this imbalance exists remains a key research question. It may relate to the initial density of the molecular cloud or the influence of past supernova events that the gas. Each new dataset collected from Orion reshapes the framework of stellar evolution. What was once a mythic pattern in the sky has become a precision-tested model for how the universe recycles itself. The story of Orion's discovery now extends beyond observation to active investigation, a continuous process that refines the boundary between what is known and what remains to be explained. The nebula no longer represents a mystery of mythology, but a living record of astrophysical processes, still unfolding, still revealing the mechanisms that govern how stars, and by extension, life, come to be. There is an unavoidable tension at the heart of every great discovery, a quiet unease that comes from realizing that beauty, when observed closely enough, is often built on violence. The scientists who turned their eyes to the Orion Nebula came face to face with this paradox. What they saw was not a tranquil cradle of light, but a furnace. Within its heart, the most fundamental act of creation in the cosmos, the birth of stars unfolded through collapse, compression, and destruction. For many, it was a moment of both triumph and discomfort. The universe's most nurturing act was also its most brutal. In the earliest days of astrophotography, when Charles Messier catalogued the object that would later bear the name M42, he described it simply as a faint patch of light. He could not know that behind that glow, hydrogen clouds were collapsing under their own weight with pressures beyond comprehension, or that within that same light lay the seeds of future planets. For him, and for those who followed, each improvement in observation brought both clarity and contradiction. As technology sharpened the image, the illusion of serenity faded. What replaced it was motion, heat, and conflict. The scientists who first grasped the scale of these processes often spoke not of wonder, but of humility. The nebula revealed that creation and destruction were not opposites, but partners, two sides of the same equation. This realization challenged long-held human instincts that associated creation with peace and destruction with loss. In Orion, the two were inseparable. Every new star consumed the gas that might have birthed others. Every shockwave that cleared a path for light also extinguished weaker formations. It was a form of order built from entropy, a balance maintained by instability. Philosophers and physicists alike found themselves reflecting on what this meant beyond the realm of data. If life, including our own, arises from such turmoil, then perhaps the human condition mirrors the same logic. Growth through struggle, order through collapse. The same thermodynamic laws that sculpt stars may, in an abstract way, govern the unfolding of thought and civilization. The concept was both disquieting and liberating, that chaos could be the engine of meaning itself. For those who devoted their lives to studying it, the conflict was personal. Observers like Edwin Hubble and Henrietta Leavitt, though separated by time, shared an emotional distance from the objects they measured. Their instruments captured the raw mechanics of the cosmos, but behind the data lay a recognition of something larger, a pattern that echoed human emotion. The collapse of a gas cloud into a star resembled the collapse of uncertainty into understanding. Each observation, each refined measurement, was its own act of transformation. The engineers and scientists who built the James Webb Space Telescope carried this same burden into the modern era. They were not only building a machine, they were extending the human gaze into epochs of formation and annihilation. Many of them spoke of the emotional strain of constructing something designed to outlive its creators, a telescope meant to witness the earliest light of the universe. Long after its makers were gone, the pursuit of knowledge, in this context, became a reflection of the same cosmic pattern, a generation creating something powerful enough to illuminate what it would never personally see. Behind every calculation lies a quiet human element, the awareness that to study creation is to confront destruction. When scientists simulated star-forming regions, their equations predicted not harmony but turbulence. Magnetic fields twisted like torn fabric. Gravity competed with radiation pressure in an unending standoff. In computer renderings, the beautiful symmetry of the nebula dissolved into vortices and fractures. And yet, from that chaos, stable stars emerged. It was a paradox that could not be resolved through mathematics alone. The philosophical weight of Orion's revelations reached beyond astronomy. It forced a reconsideration of what life and order truly mean. If the building blocks of existence arise from instability, then perhaps perfection is not the absence of chaos, but the ability to persist within it. The universe does not strive for balance. It generates it through opposition. In Orion, the process is literal: pressure and collapse, radiation and gravity. In humanity, it becomes metaphorical: conflict and creation, destruction and renewal. And so, the scientists watching Orion's evolution came to embody the very forces they studied. Their drive to decode the nebula's mechanisms was both intellectual and existential. To them, knowledge was not just accumulation, it was participation. Each discovery was a way of aligning the human narrative with the cosmic one, as though by understanding how stars are born, they might understand why life exists at all. But emotion alone could not explain the pattern they observed. The philosophical reflections, while profound, could not substitute for physics. To truly grasp why the Orion Nebula behaves as it does, why it breeds massive stars at such extraordinary rates, why its light glows in both creation and destruction, astronomers had to move beyond emotion, beyond poetry, and confront the mathematics of chaos itself. The next stage of discovery would demand precision, a quantification of turbulence, energy, and collapse that might finally reveal how the universe builds its most violent masterpieces. The attempt to quantify chaos began with the instruments themselves. Observatories across the world turned their sensors toward Orion, measuring radiation at every wavelength imaginable. Each frequency revealed a different layer of the nebula's structure. In the infrared spectrum, astronomers saw through the obscuring dust to the dense pockets where stars were forming. In radio wavelengths, they tracked molecular hydrogen, carbon monoxide, and traces of ammonia, the building materials of stellar nurseries. The data confirmed what theory had long suggested. Turbulence was not a side effect, but a fundamental part of the process. The nebula's gases moved at supersonic speeds, colliding, fragmenting, and compressing under gravity. Within these collisions, new stars ignited. Computational astrophysics advanced to keep pace. Using vast supercomputers, scientists modeled the Orion Nebula in 3 dimensions. Each simulation ran for weeks, calculating the gravitational interaction of millions of particles. The result was a digital version of creation governed by the same physics as the real nebula. The models demonstrated that even slight variations in temperature or density could determine whether a region collapsed into a star or dispersed into empty space. Star formation, it turned out, was not a single event, but a self-regulating network of feedback loops. Massive young stars generated powerful stellar winds and radiation that both triggered and suppressed further formation. The nebula was a constantly shifting system, always on the edge of equilibrium. This understanding reframed earlier assumptions about how galaxies evolve. The violent feedback from young, hot stars was no longer seen as destructive, but as necessary. Without that energy, molecular clouds would collapse too quickly, forming unstable clusters that would burn out in cosmic moments. By introducing turbulence and pressure, these same stars ensured that new generations would form at a sustainable pace. What appeared as chaos on small scales was revealed to be a stabilizing mechanism on larger ones. Orion was not random. It was organized turbulence, a structured disorder that allowed the cycle of creation to persist. The data from the James Webb Space Telescope deepened this picture even further. Its infrared instruments mapped thousands of protostars hidden inside the nebula's dense regions. Many were surrounded by thick accretion disks, the raw material from which planets would one day form. Webb's sensitivity allowed scientists to study these disks in unprecedented detail, detecting water vapor, silicates, and carbon compounds. The discovery suggested that the ingredients for life could exist even in environments dominated by radiation and shock waves. Life, at least in potential, was not confined to calm conditions. It was forged in the same environments that sculpted the most massive and short-lived stars. For astronomers, these findings resolved one side of the paradox, while deepening another. They could now explain how violence and creation coexisted, but not why the universe operated this way. The physics described the process with precision: the energy thresholds, the collapse rates, the magnetic field alignments. Yet it could not answer the deeper question of purpose. The nebula was efficient, not intentional. Its beauty was a byproduct of thermodynamics, not design. Still, the act of observing it, of translating its energy into knowledge, gave the human story a place within it. The quantification of chaos thus became a bridge between disciplines. For physicists, it provided equations that described how matter behaved under extreme conditions. For philosophers, it offered a framework for understanding existence as an emergent property of disorder. And for those who looked up at Orion on a clear night, it transformed the familiar constellation into something vast and ongoing, a reminder that the same processes shaping stars once shaped the atoms within human bodies. By the end of this era of study, the emotional conflict that once surrounded the nebula's discovery had evolved into comprehension. The violence was no longer shocking, it was essential. The nebula's turbulence was not an accident, but a requirement for creation. Through the precision of observation and simulation, humanity learned that chaos, when measured and understood, is not the enemy of order but its source. The story of Orion was no longer a contradiction. It was a model, a universal pattern that defined everything from galaxies to life itself. In the pursuit of understanding how stars are born, Orion became the perfect laboratory, vast, visible, and alive with motion. Its gas clouds stretch for dozens of light-years, their luminous folds concealing the forces that govern creation. The earliest theoretical frameworks began with a simple premise that gravity, given enough time and mass, must eventually win. In 1902, British physicist Sir James Jeans formalized this idea into what would become the foundation of stellar formation theory, the Jeans instability. It proposed that when the mass of a gas cloud exceeds a critical threshold, gravity overwhelms the internal pressure holding it apart, initiating collapse. Yet in practice, the process proved far more complex. Real clouds, like Orion's, were not still. They churned, fragmented, and twisted under the influence of turbulence, magnetism, and radiation. As telescopes grew more powerful, the theoretical lines between order and chaos began to blur. Astronomers realized that Orion's immense beauty was not the product of symmetry, but of turbulence. Supersonic shock waves rippled through the nebula, compressing hydrogen into filaments, long thread-like rivers of gas stretching across interstellar space. Within these filaments, density variations gave rise to nodes, pockets where gravity could take hold. The turbulence that appeared to threaten structure was, paradoxically, what created it. Every eddy, every shock front, became a potential cradle for a future star. In this way, chaos became the sculptor of order. High-resolution simulations brought this idea to life, using millions of data points from observatories like ALMA and Spitzer. Researchers recreated Orion in silico, a digital universe where physics played out frame by frame. The simulations showed supersonic flows colliding, slowing, and cooling, giving birth to pockets dense enough to ignite fusion. Yet the simulations also revealed how fragile the process was. A small shift in temperature or turbulence could destroy a nascent core before it ever became a star. The birth of a sun was not inevitable, it was conditional, dependent on an environment in constant flux. Magnetic fields added another layer of complexity. Though invisible, they threaded the nebula like scaffolding, subtly guiding gas flows along unseen lines of force. Observations from the SOFIA Airborne Observatory and the Planck satellite showed that these magnetic fields were not random but organized. They acted as both guides and resistors, directing matter into narrow channels, while also preventing runaway collapse. In regions where magnetic tension was high, gas accumulated slowly, forming long-lived filaments. Where it was weak, the collapse was rapid, violent, and chaotic. Orion's architecture, its glowing arcs and dark veins, was the visible expression of this hidden magnetic order. But the nebula's environment was not passive. Once new stars ignited, their radiation transformed the very space that birthed them. Ultraviolet light ionized surrounding gas, carving out vast cavities and sending shock waves through nearby clouds. Stellar winds, moving at hundreds of kilometers per second, swept up dust and compressed distant regions into new knots of density. Star formation, it seemed, was both creative and destructive, a cycle of feedback where each generation reshaped the next. The Trapezium Cluster at Orion's heart exemplified this process. Its massive O-type stars, thousands of times brighter than the Sun, flooded the nebula with energy. Around them, protoplanetary disks were both nourished and eroded, balanced on the edge between growth and annihilation. Comparisons with quieter regions like the Taurus molecular cloud highlighted Orion's singular ferocity. In Taurus, star birth proceeded slowly, producing small, isolated suns in relative peace. In Orion, by contrast, density and radiation pushed the process to extremes. Dozens of stars formed simultaneously, often in close quarters, competing for matter and gravitational stability. Collisions and accretion events were frequent, leading to chaotic gravitational dances that could eject stars entirely from their birth clusters. Orion was not merely forming stars, it was testing the limits of stellar evolution itself. As data accumulated, a new understanding began to emerge. The nebula was not simply a collection of gases obeying physics, it was a self-regulating ecosystem. Every shock wave, every radiation front, every collapse fed into a larger equilibrium. The violence sustained the cycle. Without the disruptive feedback of massive stars, the cloud would stagnate, forming too many low-mass suns and collapsing into an inert cluster. With too much feedback, it would disperse entirely, leaving no stars at all. Orion's hyperactivity was the result of existing precisely at that delicate balance where creation and destruction feed one another in perfect proportion. This equilibrium remains a puzzle. Why Orion maintains such an exact balance, while other regions either fade or explode, is still not fully understood. Some models suggest that its position along the Orion arm of the Milky Way exposes it to periodic waves of compression from nearby spiral density waves. Others propose that remnants of ancient supernova continually seed the region with turbulence, maintaining its unstable energy. Whatever the cause, Orion persists as a living model of cosmic dynamism, a place where physics and poetry converge, where the universe demonstrates that its most violent acts are also its most creative. And yet, even after decades of observation and simulation, one question remained unanswered. Why Orion, among all nurseries, burns brighter and fiercer than almost anywhere else in the galaxy as new instruments extended human vision into wavelengths invisible to the eye? Orion's complexity deepened further. Observations in submillimeter and radio frequencies revealed that beneath its luminous shell lies a dense network of cold molecular gas, a reservoir of material stretching across hundreds of trillions of kilometers. Within these regions, temperatures fall below 20 Kelvin, just a few degrees above absolute zero, allowing hydrogen molecules to bond and accumulate. These cold zones are the birthplace of the densest cores, where gravity slowly dominates over pressure and collapse begins. Using ALMA's interferometric arrays, astronomers mapped these cores in extraordinary detail, discovering that their shapes are far from spherical. Instead, they resemble flattened disks or elongated filaments, shaped by competing flows of gas and magnetic tension. Chemical tracers provided another layer of insight. By analyzing emissions from molecules such as carbon monoxide, ammonia, and formaldehyde, researchers could trace the flow of material through Orion's complex structure. The ratios of isotopes revealed how turbulence mixes gas on both small and large scales, redistributing heat and momentum across light years. It became clear that star formation in Orion is not localized, but collective. Individual cores influence one another through shared shock fronts and gravitational pull. In effect, Orion operates as a single, interconnected system, where every fragment of gas is part of a larger cycle of compression, ignition, and dispersal. High-energy observations from NASA's Chandra X-ray Observatory revealed another hidden aspect: intense radiation produced by magnetic reconnection and accretion shocks around young stars. The data showed that even in their earlier stages, protostars emit powerful bursts of energy, altering the chemical balance of their surroundings. X-rays ionize molecular gas, triggering complex reactions that form new compounds, including organic molecules. This discovery connected stellar physics to prebiotic chemistry, suggesting that the violent radiation in Orion may also create ingredients necessary for life. The scale of interaction in Orion also became more apparent through proper motion studies. Over decades of observation, astronomers tracked individual stars, mapping their velocities through the nebula. Some were found moving at extraordinary speeds, runaway stars, likely ejected through gravitational encounters with larger bodies or multi-star collisions. These ejections not only shaped the distribution of mass within Orion, but also seeded the surrounding regions with new sources of radiation and shock. The nebula's structure, therefore, was never static. It expanded and evolved continuously, sculpted by internal feedback and external motion. Simulations integrating magnetic fields, turbulence, and radiation feedback began to reproduce this dynamic behavior with increasing accuracy. Researchers found that massive stars form preferentially in clustered environments like Orion, where gravitational potential wells are deep and mass inflow is sustained. In such conditions, accretion occurs rapidly, allowing protostars to grow to immense sizes before radiation pressure halts their growth. This explains Orion's abundance of short-lived high-mass stars compared to quieter regions. However, these same stars destabilize their environments, ensuring that the next generation forms under altered conditions. The result is a self-modifying system, an ongoing dialogue between order and disruption. Recent observations from the James Webb Space Telescope added the most detailed perspective yet. Its infrared vision pierced through thick dust layers, revealing hundreds of faint low-mass protostars previously hidden from view. Many displayed protoplanetary disks, circular structures of dust and gas that may one day evolve into planetary systems. These discoveries showed that even within a region dominated by radiation and shock waves, stability can emerge on smaller scales. Planet formation begins amid turbulence, suggesting that systems like ours might owe their existence to the same violent processes once thought to prevent them. Every data, from X-ray to infrared, built toward a single conclusion. Orion's energy is not chaos without purpose. It is equilibrium in motion, a natural outcome of competing physical laws reaching a temporary truce. Gravity pulls inward, radiation pushes outward. Magnetic fields twist and resist, and turbulence spreads through every fold. Together they create a cycle where destruction sustains creation. The stars that tear apart their surroundings also ensure that future stars will form. This understanding reframed the question of Orion's ferocity. Rather than being an anomaly, its intensity might be an essential phase in galactic ecology, a necessary stage through which matter must pass to recycle itself. Supernova remnants enrich nearby gas with heavier elements, making each subsequent generation of stars and planets more chemically diverse. In this view, Orion is not merely a violent exception, but a crucial mechanism in the galaxy's evolution. It stands as both a reminder and a model that in the universe, balance often emerges not from calm, but from continuous, finely tuned unrest. At the farthest edge of human comprehension, Orion becomes not only a landscape of stars, but a boundary of knowledge itself. Every observation, no matter how advanced, meets its horizon here, where the complexity of physics folds into mystery. The James Webb Space Telescope, with its gold mirrors tuned to capture the faintest glow of infrared light, has peeled back layers of dust and gas to reveal hundreds of protoplanetary disks orbiting infant stars. Each disk, a potential solar system, spins within a battlefield of radiation and gravity. Some are circular and orderly, others fragmented and torn apart, evidence that even the earliest moments of planetary formation are defined by instability. Webb's instruments have captured the first hints of worlds emerging from chaos, their signatures hidden in the faint scattering of thermal light. It is not the image of peace, but of resilience, matter holding itself together against impossible odds. Yet, even as these images deepen understanding, they push science toward uncomfortable questions. Within Orion's Trapezium Cluster, the balance between radiation and gravity reaches its most delicate threshold. The most massive stars there emit such immense energy that their radiation pressure nearly cancels their own gravitational collapse. This razor-thin equilibrium defines a limit, the point at which creation teeters on self-destruction. If the radiation grows stronger, the star's outer layers are blown apart. If gravity dominates, collapse resumes and a heavier, shorter-lived star is born. Astronomers studying this process confront a paradox in real time. The very mechanism that allows stars to exist also guarantees their destruction. It is an elegant symmetry, power constrained by its own excess. Supernovae extend this symmetry on a galactic scale. In Orion's outer reaches, shock waves from ancient explosions ripple through the surrounding gas, compressing it into new star-forming filaments. The remnants of long-dead giants, iron, carbon, oxygen, become the seeds of future systems. Each cycle enriches the region, ensuring that every subsequent generation is heavier, richer in elements, and more capable of forming complex chemistry. The nebula sustains itself through death, a self-sustaining feedback loop that transforms decay into renewal. The heavy metals within human blood, the silicon beneath the instruments observing Orion, all trace their origin to these cycles of stellar catastrophe, but even this grand recycling may not be purely local. Some astrophysicists suspect that Orion's structure is not solely shaped by internal forces. Hidden beneath its visible beauty, it may follow the contours of something unseen, the cosmic web. Dark matter, filaments, invisible yet dominant, may guide the collapse of gas clouds along predetermined paths. In computer simulations, regions resembling Orion appear preferentially along these invisible threads, where gravitational potential is greatest. The hypothesis suggests that every glowing nebula, every nursery of stars, might be suspended from the skeleton of dark matter, the unseen architecture of the cosmos. If true, Orion's violence and order alike could be the visible expression of a framework far larger than light can reveal. Simulations attempt to capture this complexity, yet they remain haunted by imperfection. Supercomputers model trillions of particles integrating equations of gravity, thermodynamics, magnetism, and radiation. Each iteration produces astonishing visuals, filaments forming, stars igniting, disks spinning, yet no simulation can sustain Orion's full chaos. Tiny differences in initial conditions lead to wildly divergent results. Magnetic turbulence twists unpredictably. Radiation feedback fluctuates beyond stable control. Even the most advanced algorithms cannot fully reproduce what nature performs effortlessly. For scientists, this limitation is both frustration and revelation, proof that the universe is not merely complex, but inherently unpredictable, driven by processes that evade linear understanding at this threshold. Theory begins to blend with philosophy. If equations can no longer predict the precise behavior of gas and light in Orion, it raises a deeper question. Is the cosmos governed by pure determinism, or by patterns too intricate for computation to resolve? Some physicists propose that, at extreme scales, chaos becomes a creative force, not the absence of order, but the engine of diversity. In Orion, every failure of prediction births new insight. Every limit exposes a frontier. Webb's imagery, Chandra's X-rays, and ALMAS submillimeter maps do not complete the story. They reveal how incomplete understanding itself has become a tool for exploration. What emerges from these findings is a portrait of nature on the edge of self-knowledge. Orion is both laboratory and mystery, a place where the known laws of physics operate at full strength and still fall short. Gravity, radiation, turbulence, magnetism, all understood separately, yet impossible to reconcile completely when they coexist in their purest form. Humanity stands before this realization not with despair, but with reverence. The nebula is not chaos to be conquered, but a reminder that the universe's deepest truths may lie not in simplicity, but in its refusal to be simplified. And so Orion remains what it has always been, a mirror held up to the limits of perception. Every telescope aimed at it, every dataset passed through algorithms, extends the horizon of comprehension by a fraction. Yet even as clarity grows, so does the scale of what remains hidden. The more precisely science maps Orion's structure, the more it reveals an intricate balance of forces that border on the unknowable. At this boundary between explanation and enigma, the nebula stands as a quiet challenge, asking whether intelligence itself is part of the same creative turbulence it seeks to understand. To move beyond the limits of current understanding, researchers began dissecting Orion's structure in measurable terms. They focused on quantifying the forces in play rather than interpreting their beauty. The region's total mass, estimated at nearly 2,000 times that of the Sun, provided the foundation for detailed physical modeling. By measuring the velocity of gas through Doppler shifts, scientists constructed three-dimensional maps that revealed the motion of matter within the nebula. These maps showed that Orion's gas does not move randomly. It flows in coherent streams, converging at nodes where density peaks and stars begin to form. Observations with ALMA and the Very Large Telescope confirmed that these streams follow gradients of gravitational potential, aligning closely with the theoretical filaments predicted by galactic-scale simulations. At a smaller scale, magnetic field measurements offered a partial solution to one of Orion's long-standing puzzles: how such massive stars form in environments that should, by all accounts, tear themselves apart. Using polarized light from dust grains, astronomers traced magnetic field lines threading through the region. The data revealed that the fields act like tensioned cords, channeling matter toward the densest zones and providing structural support against gravitational collapse. Without this magnetic scaffolding, the nebula would disperse too quickly for massive stars to emerge. The finding reinforced the concept that magnetic regulation, not simple turbulence, determines the rhythm of star birth. Another layer of investigation focused on feedback energy. By quantifying the intensity of ultraviolet radiation and stellar winds from the Trapezium Cluster, astrophysicists calculated how much momentum and heat these young stars inject into their surroundings. The results were striking. The combined output of just a few massive stars could alter the pressure balance across entire light-years of gas. This explained why Orion's structure evolves so rapidly. Within a few 100,000 years, its internal architecture reshapes under the influence of its brightest members. The very stars that form within it also dictate when and where the next generation can emerge. In computer models, this process creates a pulsing, self-modulating system that resembles breathing on a cosmic scale. The complexity of such feedback loops presented computational challenges. To model Orion accurately, researchers had to merge fluid dynamics, radiation transfer, and chemical kinetics within a single framework, an achievement that pushes the limits of modern hardware. Even then, results remained probabilistic rather than deterministic. Small numerical uncertainties amplified over time, leading to divergent outcomes. This limitation did not represent failure, but a recognition that natural systems at this scale operate in regimes beyond stable prediction. Rather than trying to force precision, scientists began using ensemble simulations, running thousands of slightly varied models and comparing statistical outcomes. The goal shifted from reproducing a single version of Orion to identifying the patterns that consistently emerge across all versions. Parallel to these efforts, observational programs expanded across the electromagnetic spectrum. Radio telescopes mapped cold hydrogen, optical arrays captured emission lines from ionized gas, and infrared sensors traced heat from dust grains. By combining data from multiple wavelengths, astronomers created composite models of temperature, density, and composition. These revealed temperature gradients exceeding tens of thousands of degrees, from frigid molecular zones to regions near active young stars where gas is stripped of its electrons. The interplay between these extremes produced zones of instability, interfaces where star formation accelerates. The incorporation of machine learning introduced another tool for analysis. Algorithms trained on simulation outputs and observational data began identifying subtle correlations that human observers might miss. For example, certain patterns in gas velocity and magnetic orientation predicted where new stars would likely appear within the next 100,000 years. These models were later validated as new protostars were detected in precisely those regions. Such progress marked a transition from descriptive to predictive astrophysics, allowing humanity to forecast the evolution of a living nebula in real time. Despite this advancement, some aspects remain beyond confirmation. The influence of dark matter, though theoretically significant, cannot be observed directly. Its presence must be inferred through indirect gravitational effects. Yet, within the scale of Orion, these effects are too subtle to isolate. Similarly, the role of cosmic rays and quantum-level processes in regulating cloud chemistry remains a field of active debate. Each new measurement narrows uncertainty but opens new dimensions of complexity. In essence, Orion has become a working laboratory for the most advanced ideas in astrophysics, a natural experiment running continuously, indifferent to observation. The data collected from it feeds into theories of star cluster formation, planet development, and galactic evolution. Its study is not about solving a single mystery, but about defining the boundary conditions of cosmic creativity. As instruments evolve and algorithms grow stronger, Orion remains the benchmark, the test case by which every new model of the universe's machinery is measured, even as Webb's images and simulations stretched the known limits of astrophysics. Orion remained a paradox of order and disorder. The nebula's light, streaming from young, massive stars, revealed an environment dominated by radiation so intense that hydrogen atoms could barely remain intact. In this ultraviolet storm, matter was sculpted into pillars, knots, and hollow cavities, natural laboratories for physics at the threshold of chaos. Astronomers found themselves confronting not just the mechanics of creation, but the limits of prediction itself. Each simulation added precision to known laws. Yet every observation exposed a variable the models could not anticipate. Infrared mapping revealed molecular hydrogen glowing faintly in the shadowed regions behind ionization fronts. These were the dark reservoirs of gas from which new stars would emerge, hidden from optical telescopes for centuries. Inside these dense pockets, temperatures fell to just a few tens of kelvins, cold enough for molecules to cling together and gravity to begin its slow, inevitable pull. Yet the surrounding turbulence, measured through spectral line shifts, showed velocities reaching several kilometers per second. This was not quiet creation. It was a dynamic battlefield of colliding flows, where gravity, magnetism, and radiation fought for dominance. To understand this balance, researchers turned to magnetohydrodynamic models, simulations that combine plasma physics with gravity and turbulence. These revealed that magnetic fields, though invisible, threaded through Orion like scaffolding. They shaped how gas collapsed, how filaments aligned, and how entire clusters formed. Without this magnetic guidance, the nebula might have dispersed long ago, its raw material scattered by the same stellar winds that now carve its glowing edges. The fields were weak by terrestrial standards, only a few microgauss, yet across light years, they acted as the framework of cosmic architecture. Still, the puzzle deepened. Observations from ALMA and other submillimeter arrays showed protoplanetary disks, tiny, rotating structures of dust and gas, forming perilously close to radiation sources that should have destroyed them. These proplyds, as they are known, defied simple equations. Their survival hinted at feedback mechanisms not fully understood, perhaps involving shockwave shielding or localized cooling effects. It became clear that the Orion Nebula was not a static nursery, but an ecosystem, one where the death of one star could shelter the birth of another at the farthest edges of Orion's reach. Faint signatures of heavy elements told another story. This was not the first generation of stars to form here. Carbon, oxygen, and silicon lined the nebula's spectra, relics of ancient supernova that once enriched the region. The dust grains floating through the void were built from these remnants, the ashes of cosmic predecessors now seeding future worlds. Each atom carried a history older than the solar system itself, tracing an unbroken lineage of transformation from collapse to explosion, from debris to rebirth as the data accumulated. A quiet realization spread through the scientific community. The more precisely they measured Orion, the less stable its picture became. Every new layer of clarity uncovered a deeper level of complexity, suggesting that creation was not a singular process, but a continuum, a self-replicating system where chaos and structure were inseparable. The nebula was not merely a birthplace. It was a mirror of the universe's own nature, organized disorder, sustained across cosmic time. And as the last photons of Orion's light reached the detectors of Earth's most advanced instruments, they carried more than data. They carried a reminder that in chasing the limits of understanding, humanity was observing not just the birth of stars, but the reflection of its own quest to comprehend what lies beyond the reach of certainty in the quiet corridors of scientific thought. Beyond the reach of accepted models lie the theories that dare to trespass the boundaries of the known. These are not mere equations, but attempts to reach into the unknown essence of the universe itself, to ask questions that traditional science hesitates to frame. In this frontier, the Orion Nebula becomes more than a site of stellar birth. It becomes a philosophical arena where physics meets wonder, where speculation steps in when mathematics begins to falter. One such speculation begins with the dark plasma hypothesis. Some researchers, studying cosmic filaments that thread galaxies together, propose that Orion's brilliance may not stem solely from ionized hydrogen or conventional radiation mechanics. Instead, they envision a secondary plasma, a shadow network of charged particles that exists parallel to visible matter, undetectable to current instruments. This dark plasma, if real, might flow through the nebula's magnetic skeleton, feeding energy into visible structures and amplifying their luminosity far beyond what normal ionization could achieve. No telescope has yet confirmed such a phenomenon, but simulations suggest that the energy discrepancies within Orion's brightest regions could hint at something unseen, whispering through the void like a hidden current. Then there is the theory of quantum turbulence, an attempt to unite the smallest and largest scales of existence. In laboratories on Earth, quantum fluids exhibit strange, ordered vortices when disturbed, behaving like miniature versions of cosmic storms. Some physicists wonder whether the same laws could govern the motion of interstellar gas on incomprehensible scales. Could the Orion Nebula's filaments, its twisting tendrils and structured chaos, be the product of quantum effects expanded to the cosmic? If so, the turbulence within Orion might represent a bridge between quantum mechanics and gravity, the two great pillars of modern physics that still refuse to reconcile. Such an idea, though untested, offers a haunting symmetry: the birth of stars, governed by the same rules that direct the spin of an atom. More radical still is the concept of multiverse. Seeds. Certain theorists have speculated that massive nebulae like Orion may contain the raw conditions for cosmic branching, the birth not only of stars, but of entirely new universes. In this model, when a massive star collapses into a black hole, it does not simply vanish into oblivion. Instead, its singularity could act as a bridge, creating a new region of space-time on the other side, a separate cosmos governed by different constants, laws, perhaps even dimensions. If true, every nebula becomes a nursery not just for suns, but for realities. The Orion Nebula, then, might be more than a stellar cradle. It could be a cosmic womb, birthing worlds beyond reach, each carrying echoes of our own universe's origin. And beyond even this lies a hypothesis more poetic than empirical: the conscious cosmos theory. A few thinkers, operating at the edge of science and philosophy, have wondered whether the universe could possess a form of awareness, expressed through its creative processes. If matter and energy evolve toward increasing complexity from atoms to organisms, from neurons to thought, could not the universe itself be evolving towards self-recognition? In that frame, Orion's luminous clouds, its constant cycles of creation and destruction, might be interpreted not merely as physical phenomena but as expressions of cosmic cognition, a universe thinking through its own material. It is a notion that cannot be measured, yet it persists because it speaks to something primal in human curiosity, the need to find reflection in the infinite. In the end, these theories, dark plasma, quantum turbulence, multiversal birth, and conscious creation, share a single thread. They arise not from certainty but from wonder. Each represents humanity's attempt to pierce the veil between what is observable and what is meaningful. They are not answers, but mirrors of our own search for coherence in a reality that resists. Final understanding, and as astronomers continue to study Orion, recording its shifting light and evolving clouds, one truth cuts through all speculation: the elements that forged its stars are the same that form human breath, bone, and thought. The nebula's radiation, once scattered across the dark, now echoes inside every living cell. In a literal sense, and perhaps in a poetic one, humanity remains tied to Orion. We are the residue of its fire, the consciousness born from its collapse, the observers returning the universe's gaze. Amid theory and mystery, one enduring realization remains: we too are children of Orion. For scientists working to push the boundaries of understanding, the edge of speculation is not a place of fantasy but a necessary frontier. Every established principle of astrophysics once began as a question that challenged accepted reasoning. The study of the Orion Nebula continues this tradition, as researchers attempt to model, test, and quantify forces that no human can directly experience. The nebula's extreme conditions, its radiation pressure, gravitational instability, and turbulent magnetic fields, make it one of the most complex laboratories in the known universe. Each observation forces the scientific method to stretch a little further, demanding that imagination and mathematics evolve together. In recent years, attention has turned to the mechanics of plasma behavior under high radiation environments. Observations from the Hubble and James Webb Space Telescopes have shown that the ionized gases within Orion behave in ways that are not fully explained by classical models. The movement of matter appears more coordinated than expected, as if shaped by long-range electromagnetic structures rather than random turbulence alone. To explain this, some plasma physicists have begun testing new computational frameworks that merge magnetohydrodynamics with nonlinear field equations, a step toward describing how charged particles might self-organize across light-years of distance. These models are in their infancy, yet they reflect a broader shift in how scientists interpret cosmic order, not as a sequence of accidents, but as the emergent product of interaction between energy and structure at the same time. The boundaries between quantum theory and cosmology continue to blur. Laboratory experiments in cryogenic physics have revealed that quantum effects can persist at scales far larger than once believed, giving rise to stable patterns of energy flow known as quantum vortices. In the context of Orion, such effects are purely theoretical, but researchers are beginning to ask whether similar coherence could exist in regions of extreme density, where magnetic fields and radiation interact in unpredictable ways. If even a fraction of quantum stability can survive within the chaos of star formation, it may explain why nebula structures display such intricate and persistent geometry. This would imply that quantum behavior, usually confined to the microscopic, may influence the evolution of matter on galactic scales, a concept that would require rewriting large portions of current astrophysical theory. Other studies focus on the macro-level implications of energy feedback within the nebula. As new stars ignite, their ultraviolet radiation sweeps through surrounding gas clouds, triggering new waves of compression and collapse. Computer models suggest that this process operates as a repeating feedback loop, producing an ongoing rhythm of creation and destruction. In Orion, this cycle appears unusually efficient, generating thousands of stellar embryos in relatively short timescales. The physics of such efficiency remain uncertain. Some researchers suspect the influence of large-scale gravitational tides from the Milky Way's spiral arm, while others point to subtle magnetic resonance patterns within the nebula itself. Either explanation would expand current understanding of how galaxies regulate their own rates of starbirth, linking the local to the cosmic. The most speculative ideas move even further outward, questioning whether the mechanisms observed in Orion might play a role in structuring the universe itself. Certain cosmological models suggest that regions of intense star formation could influence the intergalactic medium, altering the distribution of dark matter and shaping the architecture of galaxies over billions of years. If so, Orion and similar regions would not simply be byproducts of cosmic evolution, they would be active participants, sculpting the very framework of space. Such possibilities remain unverified, but their exploration reflects the ongoing transformation of astronomy from observation into synthesis. No longer content to record what is seen, scientists now attempt to predict how the unseen behaves. Every new dataset from Webb or ALMA challenges existing models, forcing them to incorporate greater complexity, higher precision, and deeper uncertainty. The process mirrors the nebula itself, a continuous act of formation, collapse, and rebirth. In this convergence of theory and data, of speculation and rigor, Orion serves as both subject and symbol. It reminds science that discovery is not only about confirming what is already expected, but about confronting the limits of comprehension. Beyond the known equations and validated measurements, there remains a region where imagination and evidence meet fragile, uncertain, but necessary. It is here, at this threshold, that the most significant discoveries often begin, in the present age of discovery. Orion stands not only as a myth reborn, but as a laboratory in motion, a living experiment stretched across light years. For astronomers, it has become the stage upon which the story of stellar creation unfolds in real time. Where ancient civilizations once read prophecies in its glittering belt, modern science reads data wavelengths, spectral lines, molecular signatures, each carrying the coded whispers of creation itself. The Orion Nebula has become a mirror in which humanity can watch its cosmic ancestry form and dissolve. The James Webb Space Telescope, humanity's most ambitious eye into the infrared universe, now gazes deep into Orion's heart. Its detectors peer through clouds opaque to visible light, capturing the hidden birthplaces of stars where temperatures drop to mere tens of degrees above absolute zero. Within these cold pockets, gravity gathers hydrogen atoms like invisible hands shaping clay. Webb's instruments record the faint glow of heat from these embryonic suns, mapping each stage of development from diffuse dust to compact core, from collapse to ignition. The images, transformed into data and models, have revealed that Orion's star formation is not a linear process, but a chaotic ballet of forces, magnetic fields twisting like chords, radiation carving tunnels through gas, shock waves igniting new chains of collapse. Alongside Webb, the Atacama Large Millimeter-Submillimeter Array, ALMA, observes the molecular breath of Orion from a desert plateau in Chile. Its network of radio dishes detects signals from carbon monoxide, formaldehyde, methanol, and other complex molecules within the nebula. These are not mere traces of chemistry. They are the seeds of potential biology. In Orion's cold filaments, scientists have found organic molecules forming spontaneously precursors to amino acids, the building blocks of life. Each discovery deepens a timeless question. If the materials of life are forged in the same storms that birth stars, then how many worlds, beyond our own, now wait to awaken? New tools of analysis have joined the exploration. Machine learning algorithms, trained on terabytes of telescope data, now identify patterns that human observers might never detect. They can predict which dense knots of gas will collapse into stars, estimate the likely mass of those stars, and even forecast when their violent births will disrupt surrounding material. In essence, artificial intelligence has become an apprentice to the cosmos, learning the rhythms of creation that nature has refined for billions of years. Through these models, Orion's evolution can be simulated not in mythic time but in measurable sequences, the closest humanity has ever come to watching the act of creation unfold across the planet. Observatories coordinate through what is known as the Orion Project, a collaboration uniting instruments from Chile, Hawaii, Spain, and space itself. Together they assemble a living map of stellar evolution, one updated continuously as new data streams in. The result is an unprecedented chronicle of transformation, a record of cosmic weather, molecular movement, and gravitational dynamics so precise that scientists can trace the life cycles of stars from their infancy to their explosive deaths. Yet even as observation deepens, Orion reminds humanity of its limits. Within its glowing heart lie several massive young stars, each dozens of times heavier than the Sun, now nearing the threshold of supernova. Their lifespans, measured in mere millions of years, are fleeting by cosmic standards. Astronomers watch them carefully, awaiting the moment when one will collapse under its own gravity, triggering a blast bright enough to outshine the full moon. When it happens, it will not merely be a spectacle, but a renewal. The explosion will hurl heavy elements, oxygen, silicon, iron, back into the nebula, enriching it for future generations of stars and worlds. In that instant, Orion will again enact the universe's oldest ritual, the transformation of death into creation. This convergence of technology, theory, and observation marks a new era in cosmic study, one where the boundary between observer and participant grows thin. For in decoding the nebula, humanity is also decoding its own origin story. Every measurement of gas density, every model of stellar feedback, every captured photon tells the same truth. The processes that shape Orion also shaped Earth, the Sun, and the atoms that form human life. And so, while telescopes and algorithms continue their silent watch, the deeper significance remains unchanged. Orion is not a distant place, nor merely a spectacle of light and dust. It is the cosmic workshop from which existence itself draws its pattern, a reminder that the same forces now shaping new stars once shaped everything that breathes, thinks, and dreams beneath them. The cycle continues, unbroken, as the observers of creation realize they are its product. In Orion's storm, the universe looks back at itself, and in that reflection finds continuity between the birth of stars and the birth of meaning beyond the beauty of. Orion's radiant clouds lies an ongoing pursuit, grounded in precision, a mission less about wonder and more about evidence. Each observation, every data point, contributes to a vast effort to quantify the physics of starbirth. Astronomers seek measurable truths, the rate of collapse, the density thresholds for ignition, the mass limits that decide whether a forming star becomes a stable sun or collapses into failure. It is a field driven by constant refinement. Instruments once capable of detecting only broad shapes now resolve structures smaller than a fraction of a light year. Each refinement exposes new complexity and new questions. The James Webb Space Telescope continues to be the centerpiece of this exploration. Its infrared capabilities, tuned to detect wavelengths invisible to the human eye, make it uniquely suited for tracing dust-obscured processes. Webb's detectors can identify emission from polycyclic, aromatic hydrocarbons, complex organic compounds that form in the hot winds of young stars and spread through surrounding clouds. These compounds, discovered throughout the Orion Nebula, act as tracers of star-forming activity, marking regions of active turbulence. Webb's spectral analysis also helps determine the chemical ratios of hydrogen, helium, carbon, and oxygen, offering a clearer understanding of how material from previous generations of stars seeds the next dot at the same time. The Atacama Large Millimeter Submillimeter Array extends the investigation into Orion's colder regions. ALMA's millimeter wavelength sensitivity reveals the slow motions of gas filaments under gravity's pull. By measuring Doppler shifts, scientists can calculate exact velocities within the collapsing clouds. This data helps verify theoretical models of turbulence and fragmentation. It also offers new insight into why only a small percentage of nebular material ultimately becomes stars, while the majority remains suspended or is expelled by stellar winds. The numbers challenge assumptions about efficiency in cosmic creation, reminding researchers that even the universe operates with limits and losses. Meanwhile, advances in computational astrophysics allow these datasets to converge. High-resolution simulations now attempt to reproduce Orion's internal dynamics. These models require immense computing power, capable of tracking billions of interacting particles over thousands of simulated years. Researchers compare the simulated outcomes to real-time observations, searching for consistency between theoretical physics and nature's execution. Such comparisons often highlight gaps, areas where turbulence, magnetic reconnection, or radiation pressure behave unpredictably. These discrepancies drive the next cycle of research, refining equations that describe the birth of stars and planets. The integration of artificial intelligence into observational astronomy has accelerated this process further. Machine learning systems trained on Orion's data can detect faint protostars hidden deep within dust, identifying patterns that escape human analysis. They help automate the classification of objects within the nebula, from protoplanetary disks to gas voids carved by stellar winds. AI-based analysis also helps forecast how the structure of the nebula might evolve over decades, predicting new star-forming regions before they visibly emerge. These predictions are continuously tested against observations, tightening the link between theory and discovery. Scientific collaborations have become equally vital. The Orion project, an international effort connecting ground-based and orbital observatories, ensures that observations are not isolated but synchronized. Data from the European Southern Observatory, NASA, and Japan's ALMA array combine to form multi-spectrum composites, layered images that merge optical, infrared, and radio frequencies into a single dataset. This integration enables a comprehensive view of Orion, from its glowing outer layers to the dense, cold interiors where new suns are still gestating. Even with this progress, many uncertainties remain. Some of Orion's most massive stars, such as Theta 1 Orionis C, emit radiation so powerful that they distort measurements and models alike. Their ultraviolet output ionizes surrounding hydrogen on enormous scales, creating a feedback mechanism that shapes the nebula's evolution. Understanding how this radiation affects subsequent star formation remains an unresolved question. Similarly, the timing of supernova events within the region, particularly those that may have occurred millions of years ago, continues to influence models of Orion's present state. Each unanswered question ensures the field remains dynamic, open, and unfinished. The cumulative result of these efforts is not just a map of a nebula, but a deeper understanding of stellar ecosystems. Orion exemplifies how destruction and creation coexist within the same system. Observing it in real time allows humanity to study processes that once seemed eternal, now visible, measurable, and evolving within the span of a human lifetime. In this way, the Orion Nebula is not only an astronomical object, but an active experiment in universal mechanics, demonstrating how gravity, radiation, and chemistry collaborate to transform formless gas into the architecture of future worlds. And so, science continues to watch, not from myth or imagination, but through precise observation and data. The Orion Nebula stands as both a subject and a teacher, revealing that the story of star formation is still unfolding, still testing the boundaries of understanding, and still reminding humanity that within the vastness of the cosmos, even the most distant light can be traced back to its beginning in the depths of the Orion Nebula. Stars are born in silence, not from peace, but from the collapse of chaos. Clouds of hydrogen fold into themselves under the weight of gravity, heating until they ignite into light. From destruction comes brilliance, from pressure comes form, and somewhere in that rhythm, humanity finds a reflection of its own becoming. Every civilization, like every star, begins as potential, vast, formless, uncertain. Ideas gather as particles once did, colliding, merging, generating friction that gives rise to fire. Creation, whether cosmic or human, demands struggle. It is not born from calm, but from compression, from forces that threaten to tear apart what they also forge. The Orion Nebula stands as the most radiant symbol of this paradox. It is both cradle and battlefield, a place where birth and death share the same breath. When astronomers peer into Orion, they do not just see distant gas and light. They see memory, the atoms that build their telescopes, their hands, their hearts all trace back to stars that once burned and died within similar clouds. Every carbon molecule in a human cell, every trace of oxygen drawn into lungs, was once the debris of stellar annihilation. The blood that carries life carries the ashes of suns. And so, when humanity looks toward Orion, it is not looking outward, it is looking backward, into its own origin story written in plasma and dust. There is something deeply humbling in that awareness. The nebula does not ask for reverence. It simply exists, an ancient equation still unfolding. Yet, in its chaotic beauty, it reminds us of the fragility of all creation. The same processes that sculpt life also destroy it. A single supernova can erase a solar system, and yet that same explosion spreads the elements that will someday form another. The universe, indifferent and exact, creates through sacrifice. Beauty is not its goal, it is its consequence.